In the name of God, the most gracious and the most merciful. This is your teacher in statistics and probability. Today, chapter 4, which is a lesson about combinatory analysis. First, we start with sets and elements. A set may be viewed as any well-defined collection of objects, called the elements or members of the set. One usually uses capital letters A, B, X, Y to denote sets, and lowercase letter A, B, X, Y to denote elements of the sets. A membership in a set is denoted as follow. A belongs to a set S. Here, the symbol means is an element of. There are essentially two ways to specify a particular set. One way, if possible, is to list its members separated by commas and contained in braces. A second way is to state those properties which characterize the element in the set. Examples illustrating this two-way are that is A consists of the numbers 1, 3, 5, 7, 9. The second set, which reads B, is the set of X such that X is an even integer and X is greater than 0, denotes the set whose elements are the positive integers. Note that a letter, usually X, is used to denote a topical member of the set, and the vertical line is read as such that, and the comma as and. Look at this example. The set A can also be written as A is the set of X such that X is an odd positive integer and X is less than 10. We cannot list all the elements of the set B, although frequently we specify the set by this presentation, where we assume that everyone knows that we mean. Observe that 8 is an element of B, but 3 is not an element of B. Let E is the set of X and X is the solution of this equation. F is a set of two members, 2 and 1, and G is a set of 1, 2, 2, and 1. Then E equal F equal G. We emphasize that a set does not depend on the way in which its elements are displayed. A set remains the same if its elements are repeated or rearranged. Even if we can list all the elements of the set, it may not be practical to do so. That is, we describe a set by listing its elements only if the set contains a few elements. Otherwise, we describe a set by the property which characterizes its elements. Subsets. Suppose every element in a set A is also an element of a set B. That is, suppose A is an element of A implies A is an element of B. Then A is called a subset of B. We also say that A is contained in B or that B contains A. This relationship is written as follows. Two sets are equal if they both have the same elements, or equivalently if each is contained in the other. That is, A equal B if and only if A is contained in B and B is contained in A. Venn diagrams. A Venn diagram is a pictorial representation of sets, in which sets are represented by enclosed areas in the plane. The universal set U is represented by the interior of a rectangle, and the other sets are represented by disks lying within the rectangle. If I is contained in B, then the disk representing A will be entirely within the disk representing B, as in figure A. If A and B are disjoint, then the disk representing A will be separated from the disk representing B, as in figure B. However, if A and B are two arbitrary sets, it is possible that some objects are in A but not in B, some are in B but not in A, some are in both A and B, and some are in neither A nor B. Hence, in general, we represent A and B as in figure C. Basic counting principles. There are two basic counting principles used through this chapter. The first one involves addition, and the second one multiplication. Sum rule principle. Suppose some event E can occur in M ways, and a second event F can occur in N ways. And suppose both events cannot occur simultaneously, then E or F can occur in M plus N ways. Product rule principle. Suppose there is an event E which can occur in M ways, and independent of this event, there is a second event F which can occur in N ways. Then combinations of E and F can occur in Mn ways. N factorial. The product of positive integers from 1 to n inclusive is denoted by n factorial. Namely, n factorial equal 1 times 2 times 3 times n minus 2 times n minus 1 times n. Accordingly, 1 factorial equal 1 and n factorial equal n times n minus 1 factorial. It is also convenient to define 0 factorial equal 1. Let's have some examples. 3 factorial equal 3 times 2 times 1 equal 6. 4 factorial equal 4 times 3 factorial equal 24. 5 factorial equal 5 times 4 factorial equal 120. Binomial coefficients. The symbol NR read NCR or N choose R, where R and N are positive integers with R less than or equal N is defined as follows. Note that N minus R equal R. This yields the following important relation. Let's have this example. 8C2 equal 8 factorial divided by 2 factorial times 6 factorial equal 28. 10C7 equal 10C3 equal 10 times 9 times 8 divided by 3 times 2 times 1 equal 120. Permutation. Any arrangement of a set of n objects in a given order is called permutation of the object taken all at a time. Any arrangement of any r less than or equal n of these objects in a given order is called an R permutation or a permutation of the n objects taken R at a time. Consider for example, the set of letters A, B, C, and D. Then B, D, C, A, D, C, B, A, and A, C, D, B are permutations of the four letters taken all at a time. B, D, C, D, B, A, and A, D, B are permutations of the four letters taken three at a time. BC, BA, and AD are permutations of the letters taken two at a time. We usually are interested in the number of such permutations without listing them. The number of permutations of n objects taken at time will be denoted by P and R. The following theorems applies. P and R equal n factorial divided by n minus r factorial. We emphasize that there are r factors in n times n minus 1 times n minus 2 times n minus r plus 1. Permutations with repetitions. Frequently, we want to know the number of permutations of a multiset that is a set of objects, some of which are alike. We will let P, N, N1, N2, and R denote the number of permutations of an object of which N1 are alike, N2 are alike, and R are alike. The general formula follows Pn, N1, N2, and R equal n factorial divided by n1 factorial, n2 factorial, and r factorial. Let's have this example. Determine the number m of 8-letter words that may be created from the letters in the word 19. We seek the number of permutations of 8 objects of which 3 are alike, the 3 n's, and 3 are alike, the 3 is. By equation 5. M equal P833 equal 8 factorial divided by 3 factorial equal 1120. Ordered samples. Many problems are concerned with choosing an element from a set S, say with n elements. When we choose one element after another, say R times, we call the choice an ordered sample of size R. We consider two cases. Sampling with replacement. Here the element is replaced in the set as before the next element is chosen. Thus, each time there are n ways to choose an element, repetitions are allowed. The product rule tells us that the number of such samples is n times n r factors equal n power r. Sampling without replacement. Here, the element is not replaced in the set S before the next element is chosen. Thus, there is no repetition in the ordered sample. Such a sample is simply an R permutation. Thus, the number of such samples is P and R equal n times n minus 1 times n minus 2 times n minus r plus 1 equal n factorial divided by n minus r factorial. Let's have this example. Three cards are chosen one after the other from a 52 card deck. Find the number m of ways this can be done: A with replacement, B without replacement. A. Each card can be chosen in 52 ways. Thus, m equal 52 times 52 times 52 equal 140,608. B. Here there is no replacement. Thus, the first card can be chosen in 52 ways, the second in 51 ways, and the third in 50 ways. Therefore, M equal P 52 3 equal 52 times 51 times 50 equal 132,600. Combinations. Let S be a set with n elements. A combination of these n elements taken R at a time is any selection of R of the elements where ordered does not count. Such a selection is called an R combination. It is simply a subset of S with R elements. The number of such combinations will be denoted by C and R. Let's have this example. A farmer purchases 3 cows, 2 sheep, and 4 hens from a man who owns 6 cows, 5 sheep, and 8 hens. Determine the number m of options available for the farmer. The farmer has C6 3 option for cows, C5 2 options for sheep, and C8 4 option for hens. Thus, the number m of choice follows: m equal C6 3 times C5 2 times C8 4 equal 14,000. A tree diagram is a tool for listing all of the possible outcomes of a series of events, where each event can occur in a limited number of ways. The following example shows how to make a tree diagram. Let's have this example. Calculate the product set A times B times C, where A equal 1, 2, B, A, B, C, and C, X, Y. The tree is built from left to right, here with the number of branches at each point representing the various outcomes of the next event. Each tree endpoint leaf is labeled with the corresponding elements of A times B times C. M equal 2 times 3 times 2 equal 12. Finally, thank you for your attention.